Hello, hi everyone, welcome back to the series. So, in this series, we are learning binary search algorithm. We're trying different problems of binary search, and this is the one of the easiest problems of binary search, that is square root of t. It is present on the lead code and tagged as easy problem. So, let's read the problem statement. So, in this problem, we are given a non-negative integer x, and we want to return the square root of x rounded down to the nearest integer. So you know what is the square root? Square root is basically a number y when multiplied by itself gives me x. So this is the square root of y. And we are also given that this y must be non-negative, because there is a possibility that if y is negative, then negative number multiplied by negative number gives me a positive x. Fine, but those negative numbers are not allowed. We are allowed to have the only non-negative numbers. So we must not use any inbuilt exponent function or any other function. For instance, in C++ we have this power function, which basically finds the power of x, while in Python we have this type of operator, that is, which calculates the power of x. We can't use that. We have to manually write the algorithm for this problem. So let's better understand the problem statement using an example. So let's take this example. We are given input as x, which is 4. So we want to find the square root of 4. So what is the square root of 4? We know that the square root of 4 is 2. Fine. So obviously it is plus minus 2, but we just want positive numbers, so we just neglect this negative integer. So we return 2. 2 is the answer. Now how can we solve this problem using binary search? Let's see that. Okay, so let's say we are given some number x and we want to find the square root of this number. Fine, so square root of this number is, let's say, some number y, and the search space. So first of all, we need to figure out the search space. So this number y must be, so one of the observation is that this y must be smaller than x, strictly smaller than x, and it must be greater than equals to 1. So this is the search space. We want to search our integer 5, okay, not an integer, the number 5 in this search space starting from 1 till x. So this is my search space. And the second question is, are the integers are sorted? Yes, they are sorted. Since they are sorted, I can easily find out why. How? Initialize a pointer left to this point, to this end, and a pointer r to this end to perform the binary search over this search space. Fine, so that's all we have to do. How do we check? So when I calculate the mid, all I have to do, let's say the mid is m, the mid is calculated, I know, like x l, the mid, we calculate mid like this, l plus r divided by 2. This is the middle point. Then I have to check if this middle is basically equal to x divided by m. So if this is the case, then m is basically the square root of x. That's all. And then there we have another case, that is, if this m is greater than x by m, that means the answer or the square root of x lies before this m. So the boundary is reduced to L till m. So the right is reinitialized to m minus 1. While if this m is basically less than x by m, then the search space reduces to m to r. That means the left is reinitialized to m. So in this fashion, I keep on decreasing my search space, which is just the standard binary search algorithm, and eventually I find my square root of x at some point. Fine, so that's the idea. Pretty easy problem. Let's see the implementation. So this is the implementation of this my square root t function. So this is the base case when the x is basically 0, then the square root of 0 is 0. Then here is my search space, that is 1 to x. The square root of x lies within this range. Then I run my while loop. So in this while loop, I'll calculate the middle value. I check if this middle is basically the square root of x. If it is, then I return this middle right from here. If this middle value is greater than the square root that we require, then the search space is reduced from first till mid minus 1. Otherwise, the search space is reduced to middle plus 1 till last. So this is the case when the middle point that we have calculated here is less than the desired square root. Fine. So in this fashion, I will keep on decreasing my search space, and eventually I will find my answer in this last variable, and I will return this last right at the end of this function. So in this way, this my square root function is working. Let's see the time and space complexity. As we know that this is just the binary search implementation, and we know that in binary search the time complexity is log of n, while the space complexity is constant because I'm not using any extra space here. Fine, so let's see the code implementation for this solution. So this is my square root t function, which takes in the integer x and it calculates the square root t of x using binary search. So first of all, I'll handle the base condition, that is if x is basically 0, then I will return 0 right from here. Otherwise, I will define my search space, that is from 1 till last, that is x. Then I will run my while loop where the first is less than equals to so this is last, basically it's less than equals to last. Calculate the midpoint. How do we calculate midpoint? First plus last minus first divided by 2. Check if this mid is the required square root. If it is, then return the mid right from here. Otherwise, if this mid is greater than the required square root, then I have to reinitialize our boundaries, and the last is reinitialized to mid minus 1. Otherwise, the first is reinitialized to mid. Finally, I will return the last right at the end of this function, which will store our answer. So this is the simple implementation of square root t function in C++. Let's see the implementation in other languages. Okay, so this is the implementation in Java language, and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel, and stay tuned with me. Stay with me in this series. We'll be solving a lot of problems of binary search, and this playlist is going to be really helpful for you to identify these problems during contests and interview. So I'll see you in my next video.